All right, guys. So we're finishing the notes from yesterday. So today we're finishing the notes from yesterday. Now, we already did this problem here, finding the fifth root of 4a to the 8th, b to the 14th, and c to the 5th. So we already did this problem here. Now I want to look back at it and show y'all another way that we can do this. So, write this expression in simplest form. So we're taking the fifth root of this here. Now the first thing we can look at is the fifth root of 4. 5.23. So we've already done this one.
Am I blind? Yeah. I think I am. Oh, it's because I did it on the wrong thing.
Because we've already done this one.
Okay.
We're looking back at it again. Now, I think I might have an extra one. But now the first thing we're going to do is looking at this here, can we take the fifth root of 4? No. Not evenly, and there's no way to even take out a fifth.
I think everyone has to. It's just easier.
So, since we can't take the fifth root of 5, or not fifth root of 5, fifth root of 4, or simplified in any way, the 4 is going to stay inside the radical. Now the next term we're going to look at is a to the 8th. Now we can take out groups of 5, because when we take a fifth root of a variable, we're taking out kind of groups of 5 or whatever the root is. Here it would be a group of 5. So how many groups of 5a's can we pull out of a to the 8th? Well, you say 8 minus 5, which is 3, yes? So we can take one group of 5 out, yes? And we subtract 5 again? No? So the power is 8, and we can take out groups of 5 from it. So we can take out one group of 5 a's, which will just be a to the first, because we're taking the fifth root of it. And since we can't take it again, that means we have 3 left inside the radical. Questions on this here? Now we can look at b next, b to the 14th. Well, we can definitely take one group of 5 out. 9, can we take another group of 5 out? Yes, because we can do 9 minus 5, which is 4. Can we take a third group out? No, because 4, we can't subtract 5 from it nicely. So we were able to take 2 groups of 5 out, which gives us b squared. And how many are left inside? 4. And lastly, we have c. Well, c is to what power? 5. Well, 5 minus 5 is 0. So we can take one c out, and there are 0 left over inside.
How do you know whether to leave it out or put it inside?
Because this here is the number of times we can take it out, groups of 5 that we're pulling out of it. And this is our leftover. Questions on this here? And we could do the same thing with the other one here. The cubed root of 2a to the 13th, b cubed c to the 8th. Can we take the cubed root of 2? Well, no. And whatever we can't take the cubed root of stays inside the radical. The ones that we can, we bring out. Now for a to the 13th, we want to see how many groups of 3 we can take out of this. And we can do that by just subtracting 3 from 13, which gives us 10. Well, we can subtract 3 again and get 7. We can subtract 3 again, get 4. we can subtract 3 from 4 and get 1. However, I can't take 3 away from 1 and get a whole number, or yeah, a whole number. We would get an integer, we'd get a negative number. Well, how many times did I take 3 out? 4, yes? So that means we can take 4 groups of 3. We can simplify this to a to the 4th. 4 groups of 3 came out. And how many stayed inside? Whatever the remainder is, which is 1. We can do the same thing with b. B to the 3rd. Well, we'd have 3 minus 3, which is 0, yes? Can we subtract 3 again? No. So we do take 1b out. How many are left inside the radical? 0. Remainder is 0. So we just have b. And lastly, we have c. We can do 8 minus 3, which is 5. Can we subtract 5 from 3? Yes. Which gives us 2. Can we subtract 3 from 2? We can, but we don't get a nice number. We don't get a whole number. So how many times were we able to subtract 3? Twice. So 2. So we have c squared on the outside. And what's left inside is c squared. And that should match up with what we got yesterday. Yes? So this is 2 different ways to do it. And for some, this way might be a little bit easier to understand than what we did yesterday. Any questions on this here before we look at, actually continue with where we left off yesterday? So yesterday we did do this one here, x over the cubed root of y to the 8th. Now we rewrote this as a fractional exponent. And again, we could do that there, and I want to show you guys another way we can do this. So when we look at this here, the cubed root of y to the 8th is really the issue. We can't leave a radical in the bottom of a fraction. We need this to simplify. And we need this exponent inside the radical to be some multiple of the root. Now the root of this here is 3. We're taking a cubed root. So we need the exponent to be a multiple of 3, or a number that we can divide by 3 evenly. Can we divide 8 by 3 and get an integer? No. What's the next number after 8 that we can divide by 3? 9. So what we're going to do is we're going to multiply the top and bottom of this by the cubed root, because for us to be able to multiply the denominator's cubed root by something else, it needs to be a cubed root, because the only way we can multiply what's inside 2 radicals is if the radicals are the same. Well, how many more y's do I need to get from 8 to 9? 1 more, yes? So I'll multiply top and bottom by the cubed root of y. Now the reason that this is a little bit nicer is we don't have to change back from exponential to radical. Now in the numerator we have x times the cubed root of y. In the denominator, since they're both cubed roots, we can multiply what's inside them. Y to the 8th times y to the 1st would be y to the 9th. Well, the cubed root of y to the 9th, we're essentially dividing. 9 divided by 3 is 3. Or if we did it as we did in the previous one, how many groups of 3 can we take out from 9? Well, 9 minus 3 is 6. 6 minus 3 is 3. 3 minus 3 is 0. So how many groups can we take out? 3. So we would have y to the 3rd. And how many are left inside the radical? Well, 0. It's simplified out completely. So we get this here. Questions on how we did this? Is this a little bit nicer than the way we did before? Yeah. We ready to look at the other one of this type. This one here. X squared over the cubed root of y to the 13th. Now, 13 is not divisible by 3. We can't take an even groups of 3 away from 13. It just doesn't work. But we will need to multiply the top and bottom by the cubed root. And since the only term in the denominator is y, we're going to need to multiply the top and bottom of this by the cubed root of y to a power. So really we're looking for what is the first number after 13 that will be divisible by 3. What's the next number after 13 that will be divisible by 3? So 12 is divisible by 3, but it would be smaller because we want to go up. 15. Yeah, because 12 is true. Because with this here, really we can write this off to the side. Because the cubed root of y to the 13, we do indeed have 12, which would be 4, yes? So we could say that this is y to the 4th times the cubed root of y. We would have 1 left over. Does that make sense? So 12 is not wrong. It's just not the one we need. Because 15 is the next one. That is actually divisible by 3. Well, how far away are we from it with 13? 2. So I need to multiply the top and bottom of this by y squared. Now the numerator is going to be x squared times the cubed root of y squared. The denominator is going to be the cubed root of y to the 15th. Just if they, because you already went. Yes. Yeah. Now we need to take the cubed root of y to the 15th. Well, how many groups can we take out, or what would this simplify to be? Well, we can say 15 minus 3 is 12. 12 minus 3 is 9. 9 minus 3 is 6. 6 minus 3 is 3. 3 minus 3 is 0. So how many groups did we have? 5. So it simplifies to y to the 5th. Or really, we could have divided. 15 divided by 3 is 5. Because if we remember our rational exponent, it's the exponent over the root. Exponent divided by the root will get us the same thing. Any questions over this here? All right. This one here is going to be the last time we're jumping back and forth. From here on, we'll be kind of following along after this one. Write each expression in simplest form. Assume all variables are positive. So we're going to go on and divide. Now when we divide, like bases, we subtract the exponents. But before we do that, we can divide our numbers. 14 divided by 2 is 7. Now we do have like bases here. X over x to the 3/4. Now we'll subtract the exponents. Now the numerator's x is 1 minus 3/4. Y. Do we have a y in the numerator and denominator? No. So And since it is already in the numerator, we can leave it as y to the 1/3 in the numerator. And the last one we have that's not been listed is z to the -6, yes? Now, we can't leave it as a -6, but if we move it from the denominator to the numerator, the exponent will go from negative to positive, yes? So we'll have z to the 6. And if it's negative in the numerator, we can move it to the denominator to make it positive. Now we do need to simplify some things, mainly x is to the 1 minus 3/4. And what is 1 minus 3/4? So we have 7x to the 1/4, y to the 1/3, z to the 6. Do we have any negative exponents? Do we have any fractional exponents in the bottom of a fraction? Do we have any variables in the bottom of the fraction? No. So that is as simplified as it gets. Questions on this here? Yes. Sounds good. Yep, hit the wrong key. There we go. So, let's look at this one here. 16 divided by 8. And it would be in the numerator. The 16 is bigger. X is our next variable. Since the x on top doesn't have an exponent, it's understood to be. So if we subtract these here, we have 1 minus 2/3. Y is to the 1/3. And really what we're doing is we're moving everything to the numerator just so we can simplify it as best we can. And then we would readjust from there. So if one of them had been negative in the numerator after we finish simplifying, we can move it back to the denominator and go from there. Now here the 2 is fine. Now x to the 1 minus 2/3 is 1/3, y to the 1/3, z to the we could rewrite them together because I could say 2z to the 4th x y to the 1/3, but it's not really changing anything. Now if it had been x, especially if we had 2 to the 1/3, x to the 1/3, y to the 1/3, and z to the 1/3, or all of these had a 1/3 power, we could rewrite it as the cubed root back into this form, or have it in parentheses, everything to the 1/3 power. That way we can kind of group it together, but this here is just fine. So xy to the 1/3 times 2z to the 4th, this here. Oh yeah, so have 1/3 and then everything else. It would be different having 1/3 in front, because that would be considered a multiplication instead of as an exponent. But that's a good question. Any questions on this here? perform each indicated operation. So this is similar to what we started this with. Because if the radicals have the same index and the same thing inside, we can add and subtract them. So here, for A, we have 5 square roots of y plus 6 square roots of y. So we would have what? And that's it. B is the exact same thing, but we need to get the radicals to be the same. So if we look at the first one, 12 cubed roots of 2z to the 5th. So 12, yes, we are going to need to get to the 54. Now, can we take the cubed root of 2? No. Now, z to the 5th, is the exponent bigger than our index? Bigger, so it needs to be simplified. How many groups of 3 can we take away from z to the 5th? So we have z outside. How many are left over? 2. So that tells us that the cubed root in simplest form is the cubed root of 2z squared, yes? For us to be able to add or subtract, the other radical needs to be what? The cubed root of 2z squared. Exactly. So that means 54. One of its factors is 2, and the other would be 27. Now we could keep going with the factor tree, but can we take the cubed root of 27? And it is 3. Cubed root 27 is 3. So that means the 3 will come out. And if there's another number in front of the radical, we would multiply them together. But since there's not, it's just going to be 3z. Questions on this here? Any questions on how we simplified this down? Now, one thing we do need to make sure, especially with this here, is that our terms are all the same. Well, we do have the cubed root of 2z squared in both, yes? Now, they both also have to have a z in front. So the cubed root of 27.
We don't have to put it.
I mean, this 3 times 9, 3 times 3.
Oh, I see.
Yeah. So we, instead of writing it back out, we went on and simplified it. So that's a little bit of a jump from yesterday, because yesterday, guys, yesterday we did specifically write down the cubed root of 3 in there and then simplified it out. Yeah.
I'm pretty sure I knew what you did. And
Yes. Now for this here, the variables outside the radical and our radical all need to be the same for both. Because we can consider this as a single type of term, making them be the same. Now if this had been y instead of z, we're done. We can't actually add or subtract them. Yep. So 12 minus 3 is 9. Yep. Z cubed roots of 2z squared. Yes.
I only asked one.
Questions on this here? Questions on any of this here? Let's look at this one here. 6 cubed roots of x plus 2 cubed roots of x would be?
4. roots of x.
Oh.
Yeah.
I was like, am I
I'm the one.
Because since the cubed roots of x are the same in both, we can add the numbers in front, and we're done. Questions on this here? 16 fourth roots of 3p to the 6 minus p fourth roots of 48p squared. So looking at our first term, 16 fourth roots of 3p to the 6. Can we take the fourth root of p to the 6? So p to the 6, yes. But we can't take the fourth root of 3. I was meaning to say the fourth root of 3 and ended up saying, yeah, that's where I was going. Now, can we take the fourth root of p to the 6th?
Yeah.
Yes. Since the 6, exactly, since 6 is bigger than 4, we can take it. And we're going to take it one time, which will leave us with what inside the radical? 2, or p squared. And it kind of gives it to us from the problem, because if we need them to be the same, the other radical has 1p outside and 2 left inside. So for the other one, we're going to need 1p outside and 2 inside. Now so we'll still have the p, fourth root, p squared. Now we do need to simplify the 48, because our first fourth root has what inside? A 3, yes? And if we're going to be able to add or subtract, we need a 3. Right? We can divide 48 by 3, and it would be 16. So now we just need to see what the fourth root of 16 is. It's one number they like actually using, a good number. 2. Now are our expressions having the same term? P fourth root of 3p squared.
So then now you would subtract
Yes.
14
P. Radical fourth root of 3p squared, or radical.
I at least said the right answer.
All right. Questions on any of this here? Questions on anything we've done so far?
No, sir.
I like this one a lot better.
Well, we did fractional exponents yesterday, and it's a similar step, similar concept, just a little bit easier. Because if we looked at 13, the cubed root of 27 q to the 9th, well, we could plug the cubed root of 27 in the calculator and get 3. Now, we look and see for q, how many groups of 3 we can take out.
3.
So we can take 3 groups
I thought we were doing
out of q. So it gives us 3q to the 3rd. Now for this one here, we can still split it up into the top and bottom, but we're still looking at groups of 5 that we're going to take out of this here. How many groups of 5x's can we take away from x to the 10th?
2.
So it'd be x squared on top. How many groups of 5 y's can we take away from y to the 5th?
1.
This one here, we can start with the numbers. 6 divided by 3 is 2. X, we'd have 1 minus a half. Now this time, we do have a y on top and bottom. So it'd be y to the 3/4 minus 1/2. So we have 1 minus a half, which is a half. 3/4 minus 1/2 for y is And we get this here. Now the last one, we do need to simplify this. Now, square root of 9 is 3. Now we do need to simplify the square root of w to the 5th. How many groups can we take out?
1.
So what is our index here? 2.
Oh. 3.
So we can take the out
2.
2 and have how many left over? 1.
Oh, okay. I get it.
Now it's very misleading, this one here, because the other one does have a w outside. But if we look inside the radical, there are how many? 3. So we can actually bring one more w out. 3 w squared square roots of w minus w squared square roots of w is 2 w squared square root of w. Any questions on any of this here? Your homework is, if you do lose it or don't have it, it's out of the textbook. It's problems 37 through 44, 49 through 52, 57, and 59. If you notice, the worksheet that I have attached actually does have those specific problems. I just rewrote it back out so that you have those. So for the homework assignment, that worksheet, you can remove it and write specifically on it. As a worksheet, just make sure to put your name on it. I did not put a space to put a name and a little line. But you can turn that in because there is more space than the normal work or kind of book work. So you can turn that in. I did include a copy of this in Google Classroom. So if you do lose it, it is there as well. Tomorrow.